Hey everybody, today we're going to talk about logarithms and expanding and into many logs, a sum of many logs, sum of difference of many logs, and into a single log, taking it back into a single log. But first, we're going to introduce the idea of logarithms and where they come from and some properties. So let's take a look. This is the handout that I sent to you yesterday. And first we talk about what a logarithm is. So just a quick review, this is also in the Alta Newton information. So what is a logarithm? Well, if we take the exponential equation b to the y equals x, and we can rewrite this, as it turns out, as log base b of x equals y. Now note, y here is the exponent here. So the log is really just another way to write the exponent. Okay? And so it's always the log of whatever base we have of this answer, the result in this exponential equation, equals the exponent. Okay, so we should be able to take something that's written into exponent form and write it into log form. So 3 to the third equals 27 would mean log base 3 of 27 equals 3. Similarly, 2 to the minus fifth equals 1 over 32. Would mean log base 2 of 1 over 32 equals minus 5. Again, for both these examples, let's look at the form. This is the result of 3 to the third. That goes here with the log. That's the argument, if you will, of the log. The base of the exponent comes here, and the actual exponent is here. So for this one, 2 to the minus fifth equals 1/32. The base is 2. 1/32 is a result on this exponential equation, and the exponent is minus 5. So we see something like 2/3 to the second equals 4/9. We're not going to sweat it. We're going to write this as log base 2/3, because that's our base here in this exponent equation, equals 4/9, because that's the result in this exponent equation. I'm sorry, of 4/9, not equals 2, the actual exponent. We use a base 10 number system. So the common log of 10 to the y equals x is written in base 10 as log of x equals y. If there's no base written here, you can assume it's the common log. It's a base 10. Okay. And then the natural log, again, earlier in section 9.1, we talked about the number e. So e to the y, that exponential number e to the y equals x. We can rewrite as a natural log, or ln of x equals y. Properties for logarithms, whether they're natural logs or common logs or any base, the log base b of b equals 1. So if the base and the thing we're taking a log of are the same, it equals 1. The log base b of b to the n equals whatever that exponent is. And log base b of 1 always is 0. You cannot take the log of 0. It's undefined. 0 is not in the domain of a logarithm, nor is a negative number. So in other words, I can't take the log of -3. That's not in the domain. Okay, the domain of a logarithm is always greater than or equal to, greater than rather 0. Okay, so we have some properties. The log of a product equals the sum of the logs. Think about exponents. We're multiplying two things together that have the same base. We add the exponents. That's all we're doing here. The log of a quotient equals the log of the numerator minus the log of the denominator. Again, think about exponents. When we divide two things with the same base, we subtract the exponent, numerator exponent minus denominator exponent. Then we have the log of a number risen to a power. That exponent goes in front, gets brought down and goes in front, and we take the log of whatever we had originally without the exponent. Okay, so again, why is that? Well, remember, when we have a power risen to a power in exponent rules, we multiply the two exponents together, and that's all we're doing. One exponent times the other exponent of m. So one of the things that we're going to have to do in order to problem solve is we're going to have to learn how to expand equations into several logs, sums and differences of several logs with no exponents in the argument. And we're also going to have to learn how to do the reverse. So we have 3 examples of both. So let's start with a log base b of x squared, y to the fifth, and z. Now note, with these rules, when we're expanding, there's a hierarchy that we look for. The first thing we do is we look for quotients. Something divided by something inside the argument of the log. The next thing we do is we look for products in the argument. And the last thing we do is we look for exponents. So here's our argument, x squared y to the fifth times z. There's no quotient there. So we can go past the second rule and go to the first rule. And so we're going to expand this product because x squared times y to the fifth times z. So there's three things we're multiplying together. So we're going to have three separate logs. One's going to be x squared, the other's going to be y to the fifth, and the third is going to be z. Lastly, we look to see if there's exponents in the argument. There's a square here, so we bring it in front and multiply log base b of x by 2. There's a fifth power here, so we bring that down front and multiply 5 times log base b of y. And then we have log base b of x. No exponent, doesn't change. Looking at this next example, we have log, so there's no base here, so that's the common log. So it's log base 10, it's common log of 1000 x to the fifth, y to the third. So first thing we're going to do is we're going to look for quotients. There's a quotient here. There's this 1000 x to the fifth divided by this y to the third. And so we're going to first expand it using that second rule. So I take the log of the top, 1000 x to the fifth, minus the log of the bottom, y to the third, log of y to the third. Now, inside of this set of parentheses, there's a product. So I'm going to look at that rule that deals with multiplication next. So there are two things we're multiplying together, the 1000 and the x to the fifth. So each one of those is written as a single log, and we're adding them. And then we still have that minus log y to the third. Now let's look at the exponent of 5 here. Bring the 5 down, we get 5 log of x. Bring the 3 down, we get minus 3 log of y. Where did this 3 come from that magically changed to 3? We had log of 1000 here. That 3 came from the idea that 1000 is 10 to the third. So the log of 1000 is the log of 10 to the third. If I go back up to those properties, this is just like saying log base 10 of 10 to the third is going to equal the exponent, so that's 3. So that's where the 3 came from. If we have that scenario where we can write the number as some, the two bases the same to some power inside the argument, we're going to do that. We're going to rewrite that as a number rather than a logarithm, if we can. So this next one, ln of e squared over the cube root of x squared. First, whenever you have a radical inside of a logarithmic argument, change it to exponent form. So this cube root of x squared is really the x to the 2/3 power. That's how I'm going to handle it when it's in log form. So that means that we have the ln of e squared over the cube root of x squared, which is equal to the ln of x squared, or e squared rather, over x to the 2/3. This is a quotient inside the argument. So I first expand by taking log of the top minus the log of the denominator. And so that's going to be the ln of e squared minus the ln of e to the 2/3. No multiplication inside of here. So I bring the 2 down and write it as 2 natural log e. Same thing here. I bring the 2/3 down and write it as minus 2/3 natural log x. Now, as it turns out, the natural log has a base of e. So the base here and the thing we're taking the log of are the same. So that means it's going to be 1. So it's 2 times 1, or 2. And then minus 2/3 the natural log of x. Now, when we take an expanded logarithm expression and we want to rewrite it into a single log, which is vitally important for solving logarithmic equations, we do the opposite order. So we dealt with the exponent last when we expanded. So we deal with the exponent first when we bring it back down to a single log. So we're going to bring whatever number is in front of the log back up into exponent position in the argument. Then we look at if there's addition. If we're adding two or more logs together, we write one log with the things we're taking a log of multiplied together inside the argument. And then lastly, the subtraction part, write single log, positive part over the negative part. So let's take a look at an example. We have 3 log base 3 of x plus log base 3 of y plus 3/4 log base 3 of z minus log base 3 of 2 minus log base 3 of w. What a mess. We're going to write as a single log eventually. How do we get there? Well, the first thing I'm going to do is I'm going to factor out the -1 here and here. And I'm going to write it as a quantity, a minus quantity, where we're adding the two things together inside the parentheses. So what does that look like? Well, after I factor the negative out, I have that inside the parentheses. So we have log base 3 of x, so that part didn't change, plus log base 3 of y. That part didn't change. I'm not cooperating very well. And then 3/4 log base 3 of x. That part didn't change. But here and here, I factored the negative out. And so that negative goes in front, right here. And then the log base 3 of 2 and the log base 3 of w go into parentheses with addition between them. Now we're going to use the third rule first. That's the exponent rule. So anytime we have a number in front of the log, we bring it back up to the exponent position. So we have this 3 in front of this log base 3 of x. So that means that gets rewritten as log base 3 of x to the third. There's a 1 in front of the log base 3 of y, so nothing gets rewritten there. Then we have 3/4 log base 3 of z. So this 3/4 gets put back into the exponent position for z. And then the subtraction part, there's nothing in front of the log here or here, so that part stays the same. So now we go to that first rule. I know they're out of order when you simplify. That's just the order the book uses, okay? But we go to that first rule. Wherever there's addition, we write as one log, and we take the product, multiply the arguments together of the things that were added together. So we have a log base 3 of x cubed plus log base 3 of y plus log base 3 of z to the 3/4. So that means we have an argument of x cubed, of y, and of z to the 3/4. So that means we're going to multiply those three things together inside of this single log. Over here, we have the log base 3 of 2 plus, remember we factor that negative out, log base 3 of w. So that means we're going to rewrite that as 2w inside of a single log. And then lastly, we use that quotient rule where we write a single log. Use the argument of the numerator over the argument of the denominator, the positive part over the negative part. And we get this for our answer. Let's look at another example. Here we have log base 3 of x cubed plus 3 log base y minus log base, there's no base here, I'm sorry, log of 3x cubed plus 3 log y minus log of z cubed. Using rule 3, any constant number that's in front of the log, we bring up as an exponent. So this 3 is the only one we have to worry about. So we bring that up as a y cubed. Then we look for addition. These two items, these two logs right here, whoops. These two logs right here, it's not cooperating again. These two logs right here, this log of y cubed and this log of 3x cubed are added together. So that means we're going to write that as a single log. We're going to multiply the 3x cubed and the y cubed together. Still minus the log of z cubed. And then finally, apply that rule, rule 2. And we take the quotient, numerator argument divided by denominator argument, positive argument divided by negative argument with one single log. And in the last example, we have log base 2 of the quantity x minus 3 plus log base 2 of the quantity x plus 5. Since these two are added together, we write as a single log. We take x minus 3 times the quantity x minus 5. And we simplify by FOILing that out, and we're done. Note, we never distribute the log inside of an addition or subtraction. We don't distribute it inside of a multiplication or division. Okay? The log, in fact, you can't distribute things with multiplication and division. The log is just a symbol that represents, this is another way to write an exponent. It's not something you distribute. Hopefully this helps. Have a good day. We'll see you next time.